Hello students, welcome to my YouTube channel Data Shah. Today in this lecture we'll be talking about the canonical and the standard form of the LPP. So we have already discussed formulation of the linear programming problem in the previous lectures. So just a revision, when we formulate our linear programming problem, it could be in the maximize or the minimize of the objective function subject to certain constraints. So this is how we formulate our problem into the linear programming problem. So consider the definitions of solution, feasible solution, optimal solution. So we can write the linear programming problem in the matrix format and in the form of maximize or minimize the objective function with the first equation, second equation and third equation. As first equation is the objective function, and the second and the third equation are the constraints that we have in our linear programming problem. Now, what is a solution? A solution consists of those decision variables which satisfy the equation number 2. That means which satisfy ax is less than equals to b, one of the constraints. So solution is a set of those decision variables which satisfy equation 2. Now, what is the feasible solution? Feasible solution is a kind of a solution. That means it already satisfies equation 2. So it is a solution which satisfy the non-negativity constraint, or we can say which satisfy the equation number 3. So infeasible solution would be that solution which doesn't satisfy the non-negativity constraints. So we have discussed that in the in that lecture when I have discussed about the graphical solution. Now lastly, what is an optimal solution? It's a feasible solution. That means those set of decision variables which satisfy equation number 2 and equation number 3 which satisfy our objective function, that means equation number 1. So that becomes the optimal solution. So let us consider certain questions. For example, let me take the example number 1. Maximize z 3x1 plus 2x2 subject to the constraints x1 minus x2 greater than equal to 0 and minus 3x1 plus x2 is greater than equal to 3, where both x1 and x2 are greater than equal to 0. Now we have to check whether this is an optimal solution. So to check whether this is an optimal solution, what we have to check whether it's a first of all is a solution, that means it satisfies the constraints. Second, to be the optimal solution, it must be a feasible solution. That means the non-negativity constraints must be there. And thirdly, if it maximizes the objective function, then we could say that it is an optimal solution. So this would be our equation number 1. This is equation number 2, and this is the non-negativity constraints. Now by looking at this, you could easily identify that x1 and x2 both are less than equal to 0. So if we are talking about minus 3 by 2 and minus 3 by 2, the set, it doesn't satisfy the non-negativity constraint. So straight away we are able to find out that it is not a feasible solution. If it would be a solution, then it won't be a feasible solution. So it can't be an optimal solution also. So let us consider whether it is a solution or not. So we'll just in equation number 2 we put these the values of x1 and x2. So minus 3 by 2 minus of minus 3 by 2 is coming out to be 0. So obviously it's satisfied. And the second one, that is minus 3 times minus 3 by 2 plus minus 3 by 2. That's coming out to be 9 by 2 minus 3 by 2, 6 by 2. Again, that is equal to 3. So it's greater than equal to 3, it's greater than equal to 0. So they both are satisfying the constraints in the equation number 2. So thus we can say that minus 3 by 2 minus 3 by 2 is a solution, but it is an infeasible solution. So it can't be an optimal solution. So this is the answer. So let's consider one more example where we have the minimization of the type objective function. So these are the constraints, and this is 2, and the non-negativity that x1 and x2 both are greater than equal to 0. So in this question we have so here we have 3 points given, like first one is 0, 2, second is 3, 2, half, and lastly third is 2.50. So at all the 3 points we have to check whether it is having an optimal solution, that means whether it is a solution, then feasible solution, and then lastly the optimal solution. So let us consider here. So 0, 2 as we could see here, they satisfy the constraints. So when you will in the first one, if I put 0 plus 6, it is coming out to be 6, which is greater than equal to 3. In this one it is 0 plus 2, which is equal to 2, greater than equal to 2. So it is satisfying the constraints. 3 by 2, it would be 3 by 2 plus 3 by 2, that's 6 by 2 equal to 3, so that's equal to 3 only. And 3 by 2 plus half, that's 4 by 2 equal to 2, so again it satisfies the constraints. Lastly we have 2.5 plus 0, 2.5, that is not greater than equal to 3. So here we could say that 2.50 is not a solution. Clearly the first and the second one, 0, 2 and 3 by 2, half, they are the non-negativity constraint, they are satisfying it. So here we could say thus the points in 1 and 2 are feasible solutions. So you can check for the objective function optimal solutions also, but third is not a solution. So like this we can answer the question. So now let us move ahead with the canonical form. Now what is a canonical form? Canonical form means it has certain characteristics where we talk about first one, the objective function is either of the maximization type or the minimization type in the canonical form, right? The second is we are talking about the constraints. All the constraints are either less than equal to or greater than equal to type. And thirdly, the decision variables are greater than equal to 0. So you have to consider all these 3 points in mind when we are talking about the canonical form of the linear programming problem. So before moving ahead, let us talk about another thing, that is the unrestricted variable. The unrestricted variable is that decision variable which do not carry any sign with it, right? That means we don't know whether it is positive, negative, or zero. So what we do in such a kind, when the nothing is given for the particular decision variable, we consider it to be unrestricted. So if xi is unrestricted, then we can put xi as xi dash minus xi double dash. This is not the derivative. We are not talking about the first derivative, second derivative. This is just a notation, and where your xi and xi dash, xi double dash are both greater than equal to 0. So we could identify that that would also be equal to 0. So let's consider some questions related to this. So let us consider the first example, where we have to write the LPP in the canonical form. So maximize Z is equal to 3x1 plus 5x2 plus 7x3 subject to the constraints So here we have both the constraints with the non-negativity constraints. Sorry, this was 3. So x1, x2, x3 all are greater than equal to 0. So now how could we write it in the canonical form? So the solution would be remember we have done 3 characteristics of the canonical form. The first one is either it would be a maximization or the minimization type objective function. So we have the maximization type, so the first characteristic is satisfied, so I will write it as it is. Then we talk about the constraints. The second characteristic was that the constraints must be either greater than or less than equal to type. So because we are talking about the maximization, and maximize objective function always have less than equal to constraints, so we can just transform this by multiplying by minus. So it can be written, if you multiply this by minus, it would be converted in minus 6x1 plus 2x2 minus 5x3 greater less than equals to minus 5. So now it is, if it is a maximization type, all the constraints must be in less than equal to. If it is a minimization type, it must be in greater than equal to. This is how it is done. So subject to the first one would be now less than equals to minus 5. The second constraint is already in less than equal to type, so no need to multiply the equation with any minus sign. With the non-negativity constraint, the last point, that all the decision variables must be greater than equal to 0. So this is how we can write down the solution, the answer. So let us consider one more example. Again, you have to write the LPP in the canonical form. Here we have a minimize Z subject to the constraints. So here we could see a difference in the question, the linear programming problem that was given to us. nothing is given to us about x1. That means here x1 is an unrestricted variable. So that means we assume x1 to be x1 dash minus x1 double dash, where x1 dash x1 double dash both are greater than equal to 0. So now we first write the equation, the linear programming problem, in this form. So wherever we have x1, we'll be substituting it by the x1 dash minus x1 double dash. So I'll be writing this as x1 dash, x1 double dash minus 2x2, subject to the constraints So now this is our linear programming problem. Now we'll be converting this into the canonical form. So as you could see, the canonical form would be of this. I'll write here. The canonical form, the objective function is of the minimized type. So minimization. So it is 3x1 dash minus 3x1 double dash minus 2x2, and subject to the constraints. The first constraint is the greater than equal to type, so I'll be writing it as it is. So this would be minus x1 dash. I have just opened the brackets, greater than equal to 3. The second constraint is less than equal to 4, so I'll be just transforming it in the greater than equal to type, again by multiplying the equation by minus. So it becomes minus 3x1 dash plus 3x1 double dash minus x2 is greater than equal to minus 4, and lastly x1 dash x1 double dash x2 is greater than equal to 0. So this is how I can, first we have to write the linear programming problem in the correct way, and then we'll be writing it into the canonical form. Now let us discuss about the standard form of the linear programming problem, but before that let me introduce you with the slack and the surplus variables. Now what is a slack variable? The standard form always requires the constraint to be in the equality, right? Constraints are always an equal to form. So what we do whenever we have a less than equal to constraint, we add a slack variable and convert it into a equality. So a slack variable typically represents an unused resource. It contributes nothing to the objective function value. So we'll be discussing certain examples where when we'll add the slack variable in the objective function, the cost of associated with the slack variable is 0. Then we have surplus variable. Again, to make write an LPP, canonical form of the LPP into the standard form, we always have greater than equal to constraint. So whenever we have a greater than equal to constraint, we subtract the surplus variable from it so that we can convert it into an equation. It always represents an excess above a constraint requirement level, and it contributes again nothing to the objective function. So let's consider the standard form of the linear programming problem. So please consider it. It could be, again, it has the characteristics. The first one is the objective function. It is the maximization or the minimization type, the same. The second one is all the constraints are of equal to type. So the first one, the maximization and the minimization, the constraints are, second I'll write, constraints are equal to type. First objective function is either maximize or minimization type. Third, all the decision variables are non-negative. And one more added one is that you will notice here the non-negative right hand side constants. That means the BIs that we have are, all the BIs must be greater than equal to 0. So this is very important, right? So they must be positive. So let's consider certain questions related to this. So let me consider the example where we are converting it into the standard form. Okay, so consider the LPP. Maximize Z 2x1 minus 3x2 plus 6x3 subject to the constraints. Second constraint. And lastly the third one, sorry. And the non-negativity constraints x1, x2, x3 are greater than equal to 0. So when we are converting it into the standard form, so the standard form of the linear programming problem is given by, so consider all the four characteristics of the standard form. First, it should be of the minimization or the maximization type. So it is given to us. Then we are talking about the constraints. Constraints must be of the less than equality. So when we are talking about the equality, and then the decision variables are non-negative, it is given to us. And the fourth one was the BIs must be positive. Here you will see that one of the BI is minus 7. So what we can do, we can rewrite this as, by multiplying it by minus the whole equation, we can rewrite this as less than equals to 7. So now we can convert it into the standard form. So you will notice here this is x1 plus 0 times x2 minus 3x3 is greater than equal to 4. Let me just write it in a proper manner. And this one would be 2x1 minus 8x2 plus 3x3 less than equals to 4, minus x1 minus x2, 0x3 less than equals to 7. So these are my constraints now. So in the standard form, now all the BIs are greater than equal to 0. So the first point, the BIs must be greater than equal to 0. So it's done. Second, all the constraints, the non-negativity of the constraint, that is the decision variables, must be greater than equal to 0, done. The third one, the constraints are of the equal to type, right? So we'll be doing that. So how I can write it now, whenever we have greater than equal to, we always subtract the surplus variables. So here we'll be writing x1 plus 0 x2 minus 3 x3 it equal to 4. So it would be done by subtracting s3, or I can take s1, sorry, let me take s1. Now it has a 0 cost, as I told you, so it would be multiplied, we can add it in the objective function with 0 cost, 0 times s1. Then we have the another one, 2x1 minus 8x2 plus 3x3. It's a less than equal to type, so I can make it equal to 4 only if I'll add a slack variable. So I'll be adding a slack variable s2. So this would be in the objective function. Again, it has 0 cost. Then next and the last one, minus x1 minus x2 0 x3. Again, it is a less than equal to type, so I will be adding the another slack variable s3, so it would be 0 times s3. Now lastly, how many variables do I have? I have x1, x2, x3, s1, s2, s3. All must be greater than equal to 0. So this is my standard form of the linear programming problem. So you always have to keep in mind this while transforming your linear programming problem into the standard form. So let us consider one more question, another one. Maximize z, 3x1 plus 5x2 plus 7x3 subject to the constraints So now here again you have to keep all the things in mind, the characteristics. So all the BIs are greater than equal to 0. Yes, the BIs are greater than equal to 0, the first one. Second, is all the xi is greater than equal to 0? No, we are just given that x1 and we have x3 greater than equal to 0. But what about x2? Nothing is given to us about the x2. That means it is a unrestricted variable. So if it is an unrestricted variable, so first of all, before transforming it to the standard form, first of all you have to rewrite your linear programming problem using x2 as so here let us put x2 equal to x2 dash minus x2 double dash, right? So therefore the linear programming problem is maximize z So wherever we have x2, I'll be just replacing it by x2 dash minus x2 double dash. Rest, nothing will be changed because the BIs are greater than equal to 0. So x1, x3, x2 dash, x2 double dash, all are greater than equal to 0. Now, I can convert this into now the standard form. Now, what would be the standard form of your LPP? It would be the maximize z 3x1 plus 5x2 dash minus 5x2 double dash plus 7 times x3 subject to the constraints. Now the constraints must be of the equal to type. So to make it equal to, let me just add some space here. So this would be subject to 6x1 minus 2x2 dash minus 2x2 plus double dash plus 5x3. Now this is greater than equal to. So for greater than equal to make it equal to, I have to add subtract a surplus variable. So surplus variable would be minus of s1 and the cost associated would be 0. So no effect on the objective function, as you could see here. Then for the second constraint, minus x1 3x2 dash 3x2 double dash minus 4 times x3. Now this is a less than equal to type, and to make it equal to, the constraint would be equality if I will add a slack variable. So again 0 coefficient in the zero cost in the objective function. So with the non-negativity constraints, x1, x2 dash, x2 double dash, x3, s1, s2 greater than equal to 0. So this is what we have in the standard form of the linear programming problem.